All right, so now let's go and get started with the unit circle. Before we get to the unit circle, we're going to go back to our special right triangles. And what we have here is a 30, 60, 90. Obviously, if I have an angle that's 30 degrees and 90 degrees, we know this other angle is going to be 90. And the important thing we want to remember about this is the relationships of our 30, 60, 90, because this is going to be important for us understanding the unit circle. So that's why it's our warm-up. So just remember, when we have a 30, 60, 90 triangle, we have a short leg as well as a long leg. And the relationships that we talked about and we kind of worked on in class is if the short leg is x, then the hypotenuse is 2x, and then the long leg is going to be x times the square root of 3. Okay, so what we're going to do is we are going to find the missing sides using our special right triangle relationships here. And then what we're going to do is we're going to find the sine of 30 degrees. So sine of this angle right here, and kind of see how each of these triangles relate. So they're all 30, 60, 90 triangles, but they all have a different hypotenuse. So again, if I'm going from short leg to long leg, I am going to multiply by 2. So if I'm going to go from short leg to hypotenuse, I multiply by 2. If I'm going to go from hypotenuse then to short leg, I'm going to want to divide by 2. So therefore, that's going to be 1/2. And then to go from short leg to long leg, you're going to multiply by the square root of 3. So that will give me square root of 3 over 2. Here, this would be 1, and this would be 1 or times the square root of 3. Here we'd have 3/2. And this would be 3 square root of 3 over 2. And here you'd get 2, and then you'd be left with 2 square root of 3. Okay, so basically all I did is take the hypotenuse, divided it by 2, and then I multiplied by the square root of 3. All right, so if I'm going to go ahead and find the sine of 30 degrees, remember sine is opposite over hypotenuse. So in this example, we have sine of 30 degrees. Let's actually zoom in here. Sine of 30 degrees is going to be sine. Sine is opposite over hypotenuse, so that's going to be 1/2 over 1, which is just equal to 1/2. Okay. The next one here is the sine of 30 degrees is opposite over hypotenuse, which is 1/2. Can't really do anything with that. The next one here is sine of 30 degrees, which equals square root of 3 divided by 2. In this case, what we're going to want to do is multiply by the reciprocal to get rid of that fraction down below. What the heck happened here? 3 divided by 2. Oh, that's over 3. Oops. So let's redo that. That's over 3. So divide by 3. Let's use red. Okay, now we'll multiply by the reciprocal. And obviously, any number multiplied by reciprocal is going to go to 1. And then here the 3's divide out. And again, we'll just be left with 1/2. And then last but not least, hopefully you're kind of catching a little trend here. We have sine of 30 degrees. And that's equal to 2 over 4, which simplifies to 1/2. Okay? And what I want you to recognize here is basically it doesn't matter the size of the 30, 60, 90 triangle because all of these triangles are similar. That means the ratio of their sides is the same. So when I ask the question, is that going to be the same for cosine of 30 and tangent of 30? Yes, because they're similar triangles, and that's very important. Now, the thing that we're going to get to next is which one of these is really going to make our math the, easiest, and something that we want to be uniform so we can use this for all triangles. And it ends up being that this is going to be our kind of triangle that we're going to want to use, okay? And that's going to help us with our definitions in this case. Because as you guys can see, the definition of a trigonometric function given a point where r is equal to 1 basically means like this is basically meaning that triangle. So let's go and take a look at what that means. So if I was going to draw this triangle, or let's just say, here's the triangle, right triangle, and we had 1, so therefore this is 1/2, and that's square root of 3 over 2. Okay, so if we were to draw a triangle about this, or a circle around this, okay, what's very important is you notice that this hypotenuse is the radius. So that's where we're getting this radius 1. So what's helpful about using this one, because you could make the argument that this was pretty easy to find sine, right? Just taking 1 over 2. However, for when we get into 45 degree triangles, that's not always going to be the case. And also, if you want to do the other trigonometric functions, this triangle might not be the easiest. So that's why this is going to be our preferred triangle. So basically when the hypotenuse is 1. And you can also think about this, when the hypotenuse is equal to 1, that basically means the radius is equal to 1 of some circle. Now, it's important to understand here, by creating the circle around this triangle, what we have done is we've kind of like taken note of a point. And basically, this is a point that's on the circle, right? So it has a radius of 1.
Cameron Fiore, if you are on campus, please come to the main office. Cameron Fiore, if you're here, please come to the main office. Thank you.
So it has a radius of 1, and you can see this point. Now, this point, if we don't know what that point is, we would just call this x comma y. Right? But what's important about this is we actually know this point, because we know, if we're going to think about this as a, Cartesian coordinate here, x has, this point has traveled square root of 3 over 2. Over, right? That's the length, that's the distance of that triangle that has given us that point there. And then 1/2 is going to be the distance that we've traveled up, which is the y value. So by looking at this graph, by using this 30, 60, 90, and again, this is our 30 degrees, right? Here's our 60 degrees, okay? What we've done is we can rewrite this triangle as just a point on the circle. So based on this angle. So now what we can kind of do is, if we were to look at this, we could say, oh, well, at 30 degrees, this line intersects at this coordinate point, which is square root of 3 over 2 comma 1/2. Now, what's also important about this, in this case, is when you look at this, we talked about the sine, right? The, sine of any angle is opposite, is going to be the opposite over the hypotenuse. Right? And that was true for all of these. Opposite over hypotenuse, opposite over hypotenuse. But you can notice for this one, I had to do a lot of simplifying. For this one, I had to do a lot of simplifying. Now, this one checked out good. But again, you look at this one, what was so nice about this one? When you take the opposite over the hypotenuse, it was just the opposite side, because putting anything over 1 is just going to give you that 1/2, right? So that's why understanding that having the radius equal to 1 or the hypotenuse equal to 1 really simplifies this, because what this is saying is when we're given a point on the unit circle with a radius of 1, that basically means the hypotenuse of that triangle is going to be 1. So rather than taking the opposite over the hypotenuse, we can just take the opposite side when identifying sine. That's why it's talking about the y coordinate, because the y coordinate is basically the opposite side of that triangle. And the cosine is you could say, adjacent side of that triangle, or the x value. So tangent is obviously going to be the opposite over the adjacent, right? So you can just take the y over the x. So what this does is this relates to the coordinate point for a circle when the radius is 1. But again, it's very, very important to remember that the radius has to be 1, because, remember last time we worked on finding some points where the radius was not 1, like a given coordinate point, you remember we talked about 2, 3. Well, if you were to plot that point, 1, 2, 1, 2, 3, that does not have, the hypotenuse obviously is not 1. Right? So you can't say the cosine is equal to 2 and the sine is equal to 3. It only works when the radius is equal to 1. So don't do what we previously did in our previous chapters from there. Obviously, you have to find the hypotenuse and you have to use the ratios. But when you use the right triangle, or when you use triangles where the hypotenuse is equal to 1, it makes things a lot easier. And this is basically all summarized in the unit circle. And now, obviously, this is just a graph representation of the unit circle, and I'm going to break this down further. But what you can see here is the unit circle basically has a radius of 1. And so what this has done is we have now created a multiple triangles, which again I'll show. So we've created multiple triangles that all have a radius of 1 of our special right triangles, our 30, 60, 90, and our 45, 45, 90 triangle. And what that has allowed us to do is write down all the points that would lie on the unit circle. So if we were to basically take all the special right triangles and write them, in this graph, what you would do is that would create this unit circle. So we're going to kind of talk about that, obviously working into the in the next couple examples, and that's what I'm going to do. I'm going to break down the unit circle. This is the overarching theme that you're going to want to know, but we're going to break it down here in the next couple examples. So let's go ahead and get on to that.